Morning, everyone. Hearty welcome to our PC4 lecture. Just for you to remind you, I put once more the table of contents here. We covered in the semester the introduction, covered the theorems and postulates, the variational theorem, the perturbation method, and we are currently in the topic of molecular quantum mechanics. And here we covered the electron density. There are any questions on the material covered so far? Please don't hesitate to interrupt me or write it in the chat, as always. As already also mentioned earlier, we will cover here Virial Theory and Hartree-Fock theory. These are two very important central to chemistry methodologies that deliver a lot of insight in terms of Virial and state-of-the-art in terms of Hartree-Fock. Most quantum chemical calculations nowadays based on Hartree-Fock or go beyond Hartree-Fock, but you still need Hartree-Fock as a baseline. Hopefully afterwards we still get to cover density functional theory. Half a chemistry Nobel Prize was awarded to one of the founders of density functional theory in 1998. It's one of the most cited methods in the field of sciences in general. So it goes even beyond chemistry, also in solid state physics and materials. It's being used a lot. Then we, if time permits, we'd like to briefly discuss what correlated methods are that go beyond Hartree-Fock, and then some technical details on basis sets and pseudopotentials. Basis sets are basically the functions which you plug into your series expansions. And pseudopotentials are a way to account for the core electrons in the nucleus, since those are typically not involved in the rearrangements of the valence electrons. We can actually replace them by an effective potential, and that's what we call a pseudopotential. It's also known as effective core potential. Okay, so that's a well-established technique in atomistic simulation. And finally, model chemistry, that is about navigating the trade-off between basis set size and electron correlation treatment. And this approach, the main developer of this approach, John Popel, got the other half of the Nobel Prize in 1998. Let me maybe just write their names down if you want to look them up. Walter Kohn, John Popel on the Nobel Prize in 1998. All right, today's topic is chapter 5, molecular quantum mechanics, and we will focus on the subchapter dipole moment and polarizability. Now, you should know already that dipole moments are very important for chemistry and in practice. So when you discuss the behavior of compounds, dipole moments often play a major role. Now, in classical terms, the dipole moment is a vector, mu, that sums over all your charges, right? Think of charges as atoms that have a charge, right? So each atom has a charge. So you sum over these charges, and we call charges generally Q. And the vector, the position vector of that charge, right? This product of charge times distance is the dipole moment. So it measures in how charge is being distributed. So the larger the dipole moment, as you know, the more polar your system, right? So in what our task now consists of, so I presume you know this already, right? This is introductory chemistry knowledge. Our task is now to recover this expression, to link it back to quantum mechanics, right? This expression does not fall from the skies, right? There's a reason why it looks as it does. And typically that reason is not discussed in the introductory courses. And so that's our task now, to put this on a sound footing, all right? Now, of course, your distance vector is the one of your unit vectors. And depending on notation, you can write that any way. It assumes that you're operating in some Cartesian coordinate system. Of course, you can do coordinate transforms if you'd like to, but for this discussion, we will stick to the Cartesian coordinate system. This means then that our dipole moment consists of a component mu x, mu y, mu z, right? Where your mu x is nothing else than the charges times x, mu y is charges times y, and mu z is charges times c. All right. So typically we grow up with this idea that these charges are, for example, atoms. Now, what is the charge of an atom, right? So it's really something like the following. You have your atom, let's say, with some electron density, and now you decide on some sort of volume, right? Where you say, okay, let's suppose this is the volume of atom A and atom B, and so I integrate in that volume my electron density, right? So let's say from minus infinity until R0, right? And that gives me the number of electrons on atom A. Right? Now, due to the bonding, some of these electrons from atom A could be pulled into atom B, or some electrons from atom B might be pushed into the volume of atom A. And so the nuclear charge of atom A might not necessarily be the same as the number of electrons in atom A, and that difference could be the charge of atom A, right? So this is the kind of charge people typically talk about or are referring to when talking about atomic charges. So it's the effective difference in nuclear charge and electron density that you somehow assign to a given atom. Now, we would like to do this a little bit more rigorous, right? In rigorous ways. This partitioning, right? Where do you can see this, right? Where do you draw the line between one atom or another? There's some arbitrariness in this, and so it's not properly defined, really, this atomic charge, right? There's no there are multiple valid definitions, right? Now, just because you have multiple solutions doesn't mean it's useless, or it also doesn't mean it's wrong. It just means there's more than one solution, right? So there's some arbitrariness in how you go forward, and so if you make any predictions based on that, you can get arbitrarily many predictions, right? And that of course might then be problematic if you compare to the experiment when there's only one answer. So the proper way to do this is really to go back to postulate number one in quantum mechanics. The wave function is what we need, and we also already used the Hornberg-Kohn theorem to show that the electron density plays an equally important role. So we should express these dipole moments in terms of electron densities, really, not in terms of arbitrarily defined atomic charges. So this is quite straightforward, right? So this means that our charge is actually not this atomic Q, right, this QA, but rather the charge you have at every grid point here, at every R, right? So there's a charge, and this is this electron density, right? So you have an electron density as a function of space, right? That is the electronic charge, right? But we have it everywhere in place, right, in space, right? So really the QM dipole moment then becomes an integral, right? You don't sum over your charges anymore. You integrate over space, and there you have your charge, rho of R times distance vector. Okay. So it's just a continuous analogon to what you've just seen, and it is still true that this is mu x, mu y, mu c. It is still a vector, and each vector element is the integral over rho. Mind you, rho is just a number, right? So you integrate over a number times the variable x, integral over number times variable y, integral over number times variable z. So that is really how our vector is defined now, right? Okay, any questions so far?
I'm sorry, can you just quickly explain what this ZA is again?
What? QA?
ZA
It's the
minus
charge.
N.
Nuclear charge.
Okay, I don't really get why you would subtract this.
So you have the nuclear charge are the protons, right? So let's say in carbon is 6, and then you subtract the electrons surrounding that atom, right? And that electron number you get by integrating the electron density around the atom. Right? And so that's what you do here. Right? That's the number of electrons surrounding atom A. And the difference of this number and its nuclear charge is the atomic charge of the atom in the molecule. Now, in the case of a free atom, that difference is always zero, right? Because the number of electrons in a free atom is the same as the number of protons, unless you ripped off one electron. But so usually so if you consider charge neutral molecules, well, all its composing atoms would be you would assume that they are charge neutral as well. And so in the dissociated case, all atoms have zero atomic charge, but as the atoms start bonding, imagine a hydrogen fluoride bond, right? HF. Right? Then the fluoride is much more electronegative. It will pull over some electrons from the hydrogen. So you might have an atomic charge of something like -1 or minus 0.5 or something on the fluorine, and a charge of plus 0.5 on the hydrogen. So maybe it helps to clarify also that the sum over atomic charges would be zero, right? Does that make sense?
Okay, yes, thank you very much.
No problem. So this is just, thank you for your questions again, right? This is just to get us to pick you up where you typically are in your introductory courses, the experimental parts of chemistry, and connect this to the quantum mechanics. Yes, so the comment from Mr. Rakus is correct. Yeah. All right. So this is now basically just the continuous version, but you still sort of have to believe me that this is what drops out from quantum mechanics. So we basically rendered our discrete dipole moment definition for atoms, now continuous for electron densities, but that's not quantum mechanics. That's just making things continuous. So how can we arrive at this expression from rigorous quantum mechanics? Now, what we would like to do, so from quantum mechanics, question mark, let's use perturbation theory. And that immediately then begets the question, what is our perturbing Hamiltonian? Right? What is the perturbing Hamiltonian that from which we can derive the expression for the dipole moment? Now, in perturbation theory, we typically go through the energy, right? So we expand the Hamiltonian, not any operator here. So let's focus on this energy term. And so we should use the correspondence principle to connect something like an electrical energy to our electron density. Yeah. So use correspondence principle for bringing in the classical electric energy contribution. Okay. And we call that classical energy contribution V. Okay. Okay. Now, we don't know this a priori, but what we do know is that an external electrical field exerted by, I don't know, your electrode or by another molecule flying by and being charged, right? That will exert a field, right? And so how does that field affect your system under consideration, right? That is the question. And so this is quite well defined, right? So if there is an external electrical field, and the symbol for electrical fields, and this is a little bit unfortunate, and you have to pay a lot of attention now, is capital E. Okay, so that is the same as our quantum mechanical energy. Now, fields are vector properties, right? These are vector fields, right? So it helps to put always the vector symbol on top of your field symbol, just to make sure that this is not an energy, not energy E, which is a scalar. Right. So there is an external electrical field. E is a vector field. Right. A vector field is a property. Imagine something like the electron density, but instead of having a number at every r, at every point in space, you have a vector at every point in space. Okay, that's a vector field. It's not so complicated once you think about it a little bit more. So imagine you have this electric external field, and it acts with a certain force on your charge Q, right? It will act with an electrical force, right? On charge Q. Now it's very important for you to distinguish this force from, let's say, the force on a covalent bond, of a covalent bond, right? The force of a covalent bond would be something where you look at the binding energy, right, the familiar ways, and then you look at its derivative, which looks something like this, right? And this would be dE dr, its force. That's the interatomic covalent force. Now the force on your charge Q is a Coulombic force, right? It's 1 over r to the 2, right? It looks something like this. That's the electrical force. It's a completely different force, right? And a priori, these two forces have nothing to do with each other. They result from different physics, right? So now fundamentally they are all related because at the end of the day it's all electromagnetism, but they come from different terms, right? Okay, so we have our electrical force acting on the charge Q, right? And now we can say, well, this field, right, really, this is the result of a derivative of our electrical potential energy V, right? Right. So this force, right, F equals derivative of potential with respect to displacement, right? Now, in terms of displacement, we would like to consider the Z component now. So let's consider our electrical field in Z, right? So that's some field strength, right? For instance, psi. Multiplied with the unit vector in Z. Okay. So let's assume your field is only acting in the Z dimension. Then our derivative here, right, would be dV dZ. This must be the electrical force. Now, by convention, we gave it a negative sign in the Z dimension. And now we also know that the external field is the charge over Q, right? So that comes from here, E equals F over Q, right? So if we know F, then this must be equals Q times E. So minus E C times Q. All right. So we have now three properties, right? Three quantities, which previously were maybe not that clear to you, right? You have the energy V, electrical energy V. You have the electrical field E, and you have the electrical force F. Okay. And in this last box, you see them all related to each other. All right, now this is just a derivative, so total derivative. So we can write it as a differential just as well. This means dV is equals minus EZ times Q times dZ. All right, nothing fancy here. Now we integrate this. On the left, we integrate dV. That gives us V, and it is the V in the Z connection, in the Z direction. So let's put the energy, we denote this with a Z, right? It's from the Z component. This thing must be equals minus E, and actually, I'm sorry, I'm a bit sloppy here, really. So the EZ is just this field strength. So I'll skip the vector now on the E. So we call this EZ times Z times Q. So this is the field strength. That's a constant, right? That is system independent, right? So that's what comes from the flying molecule by flying ion or from your electrode. This is your system, right? And what you have now is the spacious Z component and the charge, right? And now you can imagine what if you had multiple charges. Well, this becomes then VC equals minus EC sum over multiple charges, right? So this is what you have for multiple. And then this is just the Z component, but you can, of course, write this V also for the other components, right? Our choice of Z was completely arbitrary. You can repeat the same exercise for X, Y, and Z. Now, if you look at this long enough, you see that this is identical with the inner product of your electrical field with the classical dipole moment. Right? Now, this equation, if you had not realized it, should really bring that home, that idea that the dipole moment is important. Right? You see here the contribution to the energy due to the dipole moment in your system as soon as you have some non-zero electrical field being applied. Right? So that's a very important expression if you were not aware yet of it. And from this, it follows that if you differentiate your energy with respect to the electrical field, you get the dipole moment, or each of its components and hence the notation dV differentiating your electrical energy with respect to the external, to the electrical field, gives you the dipole moment. Right. Or your dipole moment is the response of your energy to an electric field. Right. The first order response. Right. So as you apply an electric field, the dipole moment is the slope of how your energy changes, the stronger your field. Now, mathematically, this is a problematic notation. Right. Any derivative is a fraction, and you cannot have a vector in the denominator of a fraction. That's nonsense. But by the right-hand box, it is clear how this notation is meant, right? So it's not strictly speaking the derivative with respect to a vector, but rather a vector of derivatives, right? On the right-hand side box, you have the proper definition of the vector elements. Now, you can say that the total energy is approximately your unperturbed energy plus this electric energy contribution, right? And if you differentiate that total energy with respect to the electrical field, only the dipole moment survives, right? Because E0 is independent of the electric field. It's the unperturbed one. So in other words, your dipole moment is in general the derivative, the first order derivative, the response of your system to a change in the electric field. So this is the most important physical meaning of the dipole moment. And that is really why it most certainly deserves a chapter in this course, and why you should really know about it if you do chemistry. Now, how is that dipole moment now connected to our perturbation theory, right? So we worked our way towards having the expression that links the classical energy to the dipole moment. And now we're going to plug it into our perturbation following the correspondence principle. So now we are ready . Our perturbational Hamiltonian is the contribution of the Hamiltonian to the energy. And we use the correspondence principles. So we say this is minus E times mu. Okay. So we use this. Okay. All right. And now, of course, we need to do this in quantum mechanics. So our positional variables have to become our QM variables. So in practice, this means, so this means where mu hat the sum over charges I and now, right? And so this is our QMR, right? It's the small r, not the atomic position, it's the electronic position, right? Which again, we can write formally in terms of unit vectors, where mu x is the sum over qi xi. Okay. All right. So the rest is plug and play. We now use first order perturbation theory. Right. This would be our unperturbed wave function. And we do this in the ground state. Yeah? So our unperturbed wave function with our perturbing Hamiltonian, we have to evaluate this expectation value, this matrix element. Okay. Now let's plug this in. The component, the vector of our field strength does not depend on our electrons, right? So that's just a prefactor. We can pull that out, minus E vector. And And so this is now, you would expect this integral now to also result in a vector, right? So that vector times vector inner product gives you a scalar number, right? So d tau, and now you have the dipole moment with your complex conjugate. All right. So this is the energy of the permanent electric, the static permanent electric dipole moment, right? And so this is what we call our mu qm. Right? It's a vector, and we simply substitute what we had there as a definition for mu here up here, right? Plug this in, and to do so, you see that this is a multiplicative operator, which sums basically over the positions of all the electrons, right? So Qi is charge of electron I. So that is -1, okay? So this whole thing is then minus d tau, since it's multiplicative, it's just a square times sum over Ri. And this is the same, it's minus dr rho of R vector R, as we change from tau over all electrons to R as the spatial 3D coordinates, right? So this is integral over all electrons over all electron variables. So for NE dimensions, right? If for every electron you have 3 spatial and 1 spin, while this is a 3D integral. In real space. Okay. Now we can do this see chapter 5.1 on the electron density. Okay. All right, so now we have the Qm energy, right, is to first order minus E times mu, and that is the same as E times dr rho of r. Okay. Now, excuse me, you do have to add this is the electronic, put this, and so this is just the electronic part, and you need to add also the nuclear dipole moment, because of course you don't only have electrons, you also have the nuclear charges, and your mu nuclear is simply the sum over all atoms alpha times their position. So that's classically. Okay. Are there any questions so far? Is this, I hope this is rather clear. We're going to take a little break now, and then afterwards we use the dipole moment to discuss also the polarizability. Let's resume at 11:16. Okay, let's continue. We now arrived at the, we performed the quantum derivation of the Hamiltonian in terms of the first order energy perturbation of your system, right? So we have identified the dipole moment as the system-specific prefactor to the first order change in your energy as a function of field strength. So if you have your total energy and there's some E0 unperturbed, and here is your field strength, your energy will change as you increase your field from 0. And that prefactor is your dipole moment, your first order change, right? Now there might be higher order changes to your energy, and that is related to the polarizability, which can be identified as the second order derivative. Now, but you have seen now the derivation of this expression from first principles. It is important to note that the dipole moment is, of course, crucial for intermolecular interactions, right? So if you have a dipole moment in your molecule and it meets another molecule, they will arrange such that they are aligned with opposite signs and with opposite directions in order to gain Coulombic interaction energy. And that is, of course, crucial for any molecular liquid or any molecular solid. You can imagine that the entire phase diagram, so where the melting lines and where the phase transitions occur, under which conditions, is dramatically affected by this key property of your compound, right? So mu is relevant, and that's sort of an understatement, for intermolecular interactions it is, of course, also relevant for spectroscopic properties, as you probably know as well. Keywords include selection rules, the transition dipole moment, which affects the intensity, also Fermi's golden rules. Now, the dipole moment is strongly related to symmetry. If your dipole moment does not change, for instance, it will not be, does not change in a vibration, it will not be infrared active, right? So for example, any homolytic bond will be cannot be seen in the infrared spectrum. Or if you have a vibration of a highly symmetric molecule, suppose a molecule like this one here, and this vibration conserves the symmetry, then it will also not be and it will also be inactive. All right. Now let's turn to the topic of polarizability. What we use as a symbol here is alpha. And alpha, this polarizability, as the name says, has something to do with how polarizable your system is. Now, being polarized or being polarizable are two very different things, right? So you can be very polarized, but hardly polarizable, and vice versa. So, for example, suppose system like HF has very low polarizability, it's very much polarized. A system like benzene is not polarized at all and is very polarizable. Okay, so you really have to grasp this difference, and of course, in terms of words, it's just a small change, right? So this is polarized, and this is polarizable. Now, what is polarizability? Now, suppose, so you do have, in general, you can calculate a dipole moment, right, in the absence of a field. If the dipole moment is non-zero, even if there's no field, right, you can calculate it. It will tell you how strong that the distortion, how strongly a system is polarized. And then, of course, as you switch on a field, you get, depending on the dipole moment, you get an energy change. Now, but what happens to your dipole moment as you switch on your field, right? So basically, your dipole moment here depends on the electron density, right? But as you switch on a field, that electron density should change your dipole moment. That electron density should change, it adapts to the field, and thereby your dipole moment changes, right? So what we have considered so far is the permanent, the static, the unperturbed dipole moment, right? And the polarizability allows us to go beyond that. So suppose, so what you have, it's an effect you only have in the existence of a field. So there is an external field, external electric field, which is non-egress zero, right? Then and only then there's an induced dipole moment. Okay. So that means you have a mu tot now, which is your permanent unperturbed dipole moment plus some term. And this term, again, we call the polarizability, and it is multiplied. It depends on the external field, the electric field. So the stronger the field, the stronger this effect, right? So in front of the field, there is a prefactor, but that prefactor, it turns out, is really a tensor. It's a 3x3 matrix. Also known as tensor. Yeah. So it's called a tensor of rank 2. A vector, a 3-element vector, is a tensor of rank 1. All right. So it's just a different notation to talk about tensors in these Cartesian spaces. And then, so this is the 0th first order, and then there are all higher order terms, hot. Okay, there can be more as you add, as you have a strong field, right? There can be higher order terms. So we are looking now at the first order effect upon inducing, upon applying a field, right? Now, neglecting hot, right? Neglecting the higher order terms, we can write our alpha matrix with the electric field vector as mu tot minus mu 0. Now that's a trivial rearrangement, you might say, but actually if we write this out, right, the definition for the dipole moment is the same. It's the integral of your tot electron density. So that is the electron density in the field, right? Times R minus the integral of your unperturbed electron density. Sorry, electron density is a scalar. So it's times R. All right. Now these integrals go over the same domain. It's the same molecule somewhere in space. And they also live on the same grid, on the same dimensions. So you can factor them out. And what you're left with is dr and then rho dot minus rho 0 times R. Okay. So this is really the change in the electron density that is induced by the field, right? So that is, of course, at the heart of what the field is doing, right? Think about your electron density as in terms of the wave function, right? By virtue of Hohenberg-Kohn. So your system is changed by that field, right? And that's what this difference, the field-induced difference in the electron density represents, right? So field-induced change in electron density. There is a question regarding the hard and soft acid base principles. It is closely related to the idea of polarizability. Okay, so acid and base are somewhat like dipole moments, right? How polarizable this is, and soft and hard has to do with polarizability, right? So our little example matrix here up here is intimately related to this, right? And hard is not the same as acidic, obviously. So it's important for you to distinguish this. Now, in how far is alpha and mu different from acidity and softness? The latter are really empirical heuristical concepts that were introduced in practical chemistry, right, through series of experimentations. The former are rooted in rigorous and proper quantum mechanics. So that while the latter can be useful, right, the proper formulation is really in terms of alpha and mu. Now, of course, also atomic charges are useful. Aromaticity is useful. We have many concepts in the experimental chemical sciences which are very useful, but they are either ill-defined or they are arbitrarily many definitions, and so they are not as reliable, if you wish, right? They are much more heuristic in nature. And so the chemical sciences in some degree are still a very immature science. It's not everything has been figured out yet, right? And so we still operate with some of these concepts because they are useful, right, for utilitarian reasons, but they are not really well defined. Now, in this course, so it's my job to present to you those concepts that are well defined. What you make out of this is, of course, up to you then. I hope that answers the question. All right, so we have this expression here, right? So basically, you have something like alpha E is an integral of some change in electron density at R times R. Now, if we can pull the external field on the other side, right, we can better understand what alpha is, right? And we can do this by writing out one component here. So this is still a vector, right? This is your delta mu, right? All right, so let's write this out. Let's consider X component, right? Only. And then what do we have here, right? So you have a matrix alpha XX times the X component of your field plus alpha XY times the Y component of your field plus alpha XZ times the Z component. And that thing must be equals delta mu X, okay? So we can get that, right? Works for defining alpha XX as your integral. So that is your change in rho times X, right? So that works if you have for alpha XX your change in rho divided by EX times X. And for alpha XY, you would have the change in rho over EY times X. Alpha XC dr change in rho EC times X. Okay. So this is how you can understand that alpha matrix, right? Your polarizability matrix. It is the response of your electron density, right? And so suppose you do for very small fields, right? So then you would have dE, right? This is the change in the electron density with respect to that field, right? Times the corresponding X component, right? So you have these two vectors, and they form something, something like an outer product. Actually, do something like this if you wish. Right? So that gives you this matrix, right? The polarizability matrix. All right. So I know that there was another question. If this is a problem for classical chemistry or quantum mechanics. So are you referring to the HSAB still, or? You can switch on your microphone, or?
That these concepts like acidity and aromaticity don't really have a grounding in quantum mechanics, because you have on one side a really useful concept, and I mean, is this imaginary? Is this?
No, this is science. So you observe things, right? Chemists have observed these concepts and they make good use of them. but they are not 100% reliable, right? They don't always work. You cannot, you can bet on them, right? But you cannot count on them, if you wish, right? So in this sense, when you use these chemical concepts, you're using a branch of chemistry that is not, strictly speaking, an exact science, right? You're using empirical heuristic knowledge, which you cannot at the moment explain with the laws of physics we have, right? It's not inconsistent with the laws of physics, right? So it's not a white-black thing, right? Science is not like that. Science is not true or wrong, right? It evolves, right? Some of these concepts were known beforehand, and then we devised the quantum mechanics to explain them, right? We can recover them from quantum mechanics. For instance, electrostatics was known before quantum mechanics, and so we knew about the electrostatics in molecules, let's say, and now, once quantum mechanics was introduced, these theories were checked for their coherence and consistency, and we can recover the dipole moment and the polarizability and so on in rigorous ways, meaning that there's no wiggling, there's no the proper, so the density distributions, right, the expectation values of your quantum experiments, they will do exactly what you predict, right? So you have really gathered a full understanding of nature that we do not have such an understanding for concepts such as aromaticity or HSAB, right? Which does not mean it's useless, right? Maybe you can come up with one. Actually, there's a whole bunch of interesting and fascinating papers that discuss these concepts in the light of quantum mechanics, right? And they are not wrong, right? These were not flawed experiments or flawed distributions, but it is not possible to define them in unique ways, right? Now this rapidly becomes very philosophical, right? You can ask, is there only one truth? Or should there be multiple truths? Traditionally, as a traditional scientist, natural scientist, we would argue there's only one truth, right? So there's a natural hierarchy, right? Methods that allow for multiple definitions are inherently less powerful and less predictive than uniquely defined concepts. Does that make sense?
Right, danke.
All right, so we have now derived the first and second order term of these the polarization effects, right? So you see that in your total dipole moment, there's the field, right? And so if you think back about your energy contribution, right? So yeah, so the get our V equals E times mu, right? And now we differentiate this once with respect to E. Then you write this as mu. You differentiate it twice. Then in the mu, you get the alpha. Okay. So in our little graphic, right? Your first order derivative is the mu, and the curvature would be given by your alpha. All right, with this, I'd like to conclude now this second chapter, and we can move ahead to the Virial theory. Now, the Virial theorem is something that is a very fundamental and yeah, important part of theoretical and physical chemistry. There's already, it's related to in thermodynamics to the work of Clausius, and then it was brought to quantum mechanics by Fock in the 30s. So what we are discussing now is not even 100 years old, all right? So also relating to these earlier remarks, right? The introduction of quantum concepts in chemistry is a rather new thing. The chemical sciences are much older. So you will encounter concepts of different ages and corresponding to different levels of insights into the nature of matter. Now, Fock called this, this paper, I believe it was in German, is Bemerkung zum Virialsatz. Now, this is, we will base our things on the time-independent Schrödinger's equation. That is H psi E psi, and assuming or exploiting that our Hamiltonian is a hero, and the operator A being linear and also time independent. Okay. So the principle results from simple commutator relationships. So we exploit the commuting properties of heroes. So if we write the commutator of H with some operator, then by definition, this is nothing else H A minus H. Now we change to Brian Kett. right? And now we operate to the left and to the right because it's a hero. So this means that this must be E psi A psi minus E psi A psi, which means it must be 0. Okay. So in other words, the commutator of our Hamiltonian with any other linear time independent operator A is 0. Now, that is really interesting because we can use some of the operators which we are interested in, and thanks to the Hamiltonian being a hero, we can then obtain additional relationships. Right? So that is really very exciting. Right? So this is known as the hyper-virial theory. Which is that now, typically, this theorem, so this is a generic general theorem, but when we talk about the virial theorem, we are referring to particular application of the hypervirial theorem. Okay. Oh. Thank you. There's a comment. We are missing Heugabel, psi, after first equals sign. Yes, I can see it. Yeah. Thank you. Thank you for this remark. I greatly appreciate that. You know, it's since we are recording these lectures and post them on YouTube, we'd like them to be as flawless as it's possible in a live lecture, so that they can be of good use for future students as well. All right, so we would like to consider now a particular operator A, and of course this choice, right, is now presented you directly, right, that one of the most interesting choices is presented to you directly. You should wonder, you might and should wonder why this particular choice, but you will see then later on that this is a very interesting choice. Now, of course, I do not present to you all other alternative possible choices that would have led to less interesting results, right? But of course, you're welcome to try as well. So this is quite often that you're presented with such choices, and you wonder how on earth did they think of this one first, ignoring that actually many others were tried, of course, but I won't tell you about those. So let's consider this choice. We sum over Qi and Pi, right? Now, Qi and Pi are positions and momentum, okay? So this is quite, these are the fundamental variables in Hamiltonian mechanics, right? And so it's quite natural to ask for an operator that would encode them, and using their product is also something very natural, right? And so we know in quantum mechanics that our momentum then should be minus I h bar Qi and the derivative with respect to Qi. Okay. So you have really here the variable times the derivative with respect to that variable. All right. Now I'm looking at the time. I think we have now a larger derivation in front of us. So I'd like to do that tomorrow. Maybe we simply end a little bit earlier today. Is there still any question regarding dipole moment, polarizability, or the beginning, this hypervirial theorem in this chapter? That's not the case. We'll conclude now, and I still wish you a very good day. Thank you for your attention, and I'll see you tomorrow.